Hello, everyone. Today we're going to explore something fascinating that you experience every day without even realizing it: perspective projection. Think about when you look down a long hallway. Have you noticed how it seems to get narrower as it goes further away? That's perspective at work. Perspective projection is our way of representing three-dimensional objects on a two-dimensional surface, like your paper or computer screen. It's designed to mimic exactly how our human eyes perceive the world around us. Just like when you look at a building from the street, objects in perspective projection appear smaller as they get further away from you. This isn't just an artistic technique. It's a fundamental tool used across multiple fields. Architects use it to show clients how their buildings will look, engineers use it for technical drawings, and artists use it to create realistic landscapes. The beauty of perspective projection is that it gives us the most natural and realistic representation of three-dimensional objects in a way that immediately makes sense to our brains. Now that we understand what perspective projection is, let's look at how it actually works. Imagine you're standing at a window, looking at a tree outside. If you could trace the path that light takes from every point of that tree to your eye, you'd see something interesting. All these visual rays converge at your eye. In perspective projection, we call the position of your eye the station point. Think of it as your viewing position. From this station point, we have these converging rays that travel to every part of the object you're looking at. When these rays intersect with what we call the projection plane, which could be your window in this example, they create the projected image. What makes this particularly interesting is that the further away something is, the more those converging rays have traveled before hitting the projection plane, resulting in a smaller projected image. This is exactly why distant objects appear smaller in our drawings. Remember, this isn't just a random artistic choice. It's based on the actual physics of how we see things. In our next slide, we'll break down all the specific elements that make up a perspective drawing. Let's break down the essential elements that make up any perspective drawing. Think of these as the building blocks we'll use to create realistic three-dimensional scenes. First, we have the picture plane or pages. Imagine you're looking through a giant sheet of glass. That's your picture plane. It's where your final drawing will appear. The station point, or SP, represents where you, the viewer, are standing. One of the most important elements is the horizon line, or HL. If you've ever stood at the beach, you've seen this. It's where the sky seems to meet the earth. In perspective drawing, this line always represents your eye level. Then we have vanishing points, or VP. Have you ever looked down railroad tracks? Notice how they seem to meet at a point in the distance? That's a vanishing point. All parallel lines in your drawing will appear to converge at these points. The ground line, or GL, is where your picture plane meets the ground. Think of it as the bottom edge of that imaginary sheet of glass you're looking through. We also have what we call the cone of vision. Imagine a flashlight beam spreading out from your eye. Anything within this cone is what you can see clearly. Finally, the line of sight is like a laser beam from your eye to any specific point you're looking at. Understanding these elements is crucial because they work together to create the illusion of depth in our drawings. In our next slide, we'll see how these elements combine in different types of perspective drawings. Now that we know our basic elements, let's explore the three main types of perspective projection. Each one has its own unique use case and creates a different feel in your drawings. Let's start with one-point perspective. Imagine you're standing in the middle of a long, straight road. All the lines parallel to your line of sight, like the edges of the road, converge at a single point straight ahead. This type is perfect for drawing corridors, railway tracks, or anything viewed head-on. Next, we have two-point perspective. Picture yourself standing at the corner of a building. Now you have lines converging at two different points on your horizon line. This gives us that classic architectural view and is incredibly useful for drawing objects that show two sides, like buildings or boxes viewed from an angle. Finally, there's three-point perspective. This is what you'd see if you were looking up at a skyscraper from street level or down at a city from a helicopter. All lines converge at three different points, creating a dramatic, dynamic view that can make objects appear monumental or diminutive depending on your viewpoint. Each of these types has its place in your artistic toolkit, and knowing when to use each one will help you create more realistic and impactful drawings. Let's walk through the step-by-step process of creating a perspective drawing. Think of this as your roadmap to creating realistic three-dimensional scenes. We start by establishing our perspective elements. First, draw your horizon line. Remember, this represents your eye level. Then, depending on whether you're using 1-point, 2-point, or 3-point perspective, mark your vanishing points on this horizon line. Next comes the picture plane, where we'll draw the front face of our object in its true shape. This is like taking a snapshot of the object straight on. From here, we draw what we call receding lines. These are the lines that create the illusion of depth by connecting the corners of our object to the appropriate vanishing points. Think of these lines as the guidelines that will help us maintain proper perspective. The next crucial step is defining depth. Along these receding lines, we mark points that determine how far back our object extends. This is where we decide if we're drawing a shallow box or a deep room. Then we connect these depth points to create the back face of our object. Finally, we add any details, textures, or additional features that bring our drawing to life. Remember, this procedure is like building blocks. Each step builds on the previous one, and skipping steps can lead to incorrect perspective. In our next section, we'll look at some real-life examples where these principles are applied. Perspective projection appears in architectural visualization, showing clients realistic views of buildings before they're built. In road design, engineers use it to visualize how roads will look to drivers, enhancing safety. Artists and photographers rely on perspective for natural compositions. Engineers use perspective drawings to demonstrate complex machinery and interactions, aiding designers and technicians. Perspective projection is vital in gaming and animation for creating immersive 3D environments. In education, it helps students understand spatial relationships of structures. Urban planners use it to visualize cities and neighborhoods, aiding in better development decisions by providing realistic previews. Perspective projection provides realistic and visually appealing representations, helping communicate design ideas. It aids in understanding spatial depth in architecture and urban planning. However, creating accurate drawings is complex and measurements aren't true to scale, requiring both perspective and orthographic drawings for precision. Proper setup of perspective elements is crucial to avoid distortions. Example of perspective projection. To draw a room using 1-point perspective, start with the horizon line at eye level and mark a single vanishing point. Sketch the front wall in its true shape, then draw receding lines from each corner to the vanishing point for walls, floor, and ceiling. Mark depth along these lines, complete the back wall, and add details ensuring all parallel lines point to the vanishing point. Now, let's explore a more technical approach to perspective drawing, the visual ray method. Imagine you're standing at a fixed point. This is your station point, and you're looking at an object through a transparent screen, your picture plane. The visual ray method works by tracing imaginary lines from your eye to various points on the object you're drawing. Each of these visual rays intersects with your picture plane, creating points that will form your perspective drawing. It's like capturing a 3D object by mapping where each of its points would appear on a window you're looking through. Let's break down the steps. First, we establish our station point. This is where we, the observer, are standing. Then we define our picture plane, which is like setting up an invisible window between us and our object. Next, we trace visual rays from our station point through all the important points on our object, corners, edges, and any other significant features. Where each of these rays intersects with our picture plane, we make a mark. These intersection points will eventually connect to form our perspective drawing. Think of it like creating a connect-the-dots drawing, where each dot is precisely placed based on where these visual rays pierce our picture plane. This method might seem more mathematical than artistic, but it gives us incredibly accurate perspective drawings. It's particularly useful when we need precise perspective representations of complex objects. Let's explore how the visual ray method is applied in real-world scenarios. This method is crucial for precision in manual perspective drawings, like having X-ray vision to see how each part of an object should be represented. Imagine projecting a transparent cube from your station point. You draw visual rays to each corner, creating points on your picture plane that form the perspective drawing. This method helps us understand the relationship between what we see and how we represent it, making it especially useful for teaching perspective drawing by demonstrating why objects appear the way they do. Let's shift our focus to another fundamental approach, the vanishing point method. This method builds on a fascinating phenomenon you've probably noticed in real life. When you look down a long straight road or hallway, the parallel lines appear to meet at a point in the distance. This is the principle that makes the vanishing point method so intuitive and effective. The process begins with drawing your horizon line, which represents your eye level. Then, depending on whether you're creating a 1-point, 2-point, or 3-point perspective, you'll place your vanishing points along this horizon line. For instance, in a 1-point perspective, you might have a single vanishing point directly ahead, perfect for drawing a corridor. In 2-point perspective, you'd have 2 vanishing points on either side, ideal for showing the corner of a building. Think of these vanishing points as magnets that pull all parallel lines toward them. If you're drawing a building, all horizontal lines running away from you will converge at these points. This creates that convincing sense of depth that makes your drawings look three-dimensional on a flat surface. After establishing your vanishing points, you'll draw the front face of your object in its true shape. This is the only part of your drawing that won't be distorted by perspective. From there, you'll draw lines from each corner toward the appropriate vanishing points, creating a framework for your entire drawing. The vanishing point method is widely used in real-world applications, particularly in architecture, to create visualizations that help clients understand how buildings fit into their surroundings. It is also powerful for interior views, showing how a room feels, light flow, and furniture fit. For example, in drawing a road, lines from 2 vanishing points create the road's edges, with elements like trees becoming smaller towards the vanishing points, creating a sense of distance. This method is valuable in engineering and artistic rendering for creating accurate, believable perspectives quickly. Comparison of visual ray method and vanishing point method. The vanishing point method acts like a GPS, guiding with specific reference points, making it fast and intuitive for architectural drawings and larger projects. It is ideal for quick visualizations. The visual ray method, akin to surveyor's equipment, is more analytical and precise, suitable for exact projections and teaching perspectives mathematical principles. These methods complement each other. The visual ray method provides the theory, while the vanishing point method offers practical application, essential for a complete understanding of perspective drawing. Example illustration. Projecting a cylinder using the visual ray method involves drawing visual rays from the station point to key points on the cylinder, creating ellipses and lines forming the cylinder in perspective. Contrasting this with the vanishing point method, a rectangular prism's front face is drawn as a rectangle, with lines extending towards a vanishing point creating the illusion of depth. These approaches achieve the same goal of creating a three-dimensional image on a flat surface, with the visual ray method offering detailed understanding and the vanishing point method providing a quicker, practical approach. Transforming three-dimensional objects into two-dimensional representations is fundamental in engineering. This process communicates design intent, guides manufacturing, and provides essential documentation. It preserves the object's geometry, dimensions, and spatial relationships, creating a detailed map that others can follow to understand or recreate the object perfectly. This skill is the foundation of modern design and manufacturing processes. We can represent 3D objects in 2D through various methods. Orthographic projections show true shapes from different angles. Isometric projections tilt the object to show three faces simultaneously. Sectional views reveal internal features by slicing the object. Perspective projections mimic human perception for realistic views. And oblique projections compromise by showing the front face true to size while other faces are at an angle. Each method has its strengths and specific uses in technical communication. To convert a 3D object to a 2D drawing, we select the projection method based on what we need to communicate. Consider the orientation to showcase important features, identify and highlight essential edges and surfaces, systematically transfer features to the 2D surface, and add dimensions and annotations for clarity. Every step should enhance understanding of the object. Challenges in converting 3D to 2D include loss of depth information, clarity in representation of overlapping or hidden features, and maintaining accuracy. Multiple views or additional notations help fully communicate an object's form, and techniques like sectional views or hidden lines ensure clarity. Precision and attention to detail are crucial throughout the process to avoid distortions. 3D to 2D conversion techniques are essential in engineering design, creating technical drawings for manufacturing and guiding the entire process. In architecture, they help create floor plans and elevation drawings for construction. In graphics, especially in game design and animation, artists work between 2D and 3D to plan and create complex animations. These techniques are versatile and crucial across various industries for designing and understanding complex structures. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.